Hello everyone, welcome to the channel Unknown Physicist. Today I am going to do problems in the paper Thermodynamics. So in this the problems will be based on first law of thermodynamics, thermodynamic process, PV diagram and sign convention. I have covered all these topics in my previous video. If you have not watched those videos, I am giving the link in the description. Please do watch them for a better understanding. Before getting into the problems, let us see the important formulas of this topic. So the first one is first law of thermodynamics, dq is equal to dw plus du. Next is the formulas for dq, dw and du and the integral form of work done, and the fourth thermodynamic process and their respective work done. Next is gamma is equal to Cp by Cv and Cp and Cv in terms of gamma, and Cp, Cv, gamma values for monatomic, diatomic and triatomic. In my previous video I have not done triatomic. For triatomic the degree of freedom is 9. Please do give a try. Before the problem, a small note. Given a PV diagram, the area under PV curve is equal to the work done, that is total work done. So let us take a thermodynamic process AB. So from A to B, that is by expansion, initial volume to final volume, and from B to A it is compression, that is from final volume to initial volume. So for the expansion curve the area are given as straight lines, and for the compression curve the area are given by dotted line. If you note, the area of expansion is less than the area of compression, so our work done here will be negative. So to easily identify this, if your thermodynamic process is in anti-clockwise direction, then your work done is negative. Now look into the next case. Here the expansion curve, the area under expansion curve A to B, initial to final volume, is represented by dotted line, and from B to A, that is compression, the area under compression curve is represented by straight line. If you look here, the area under expansion is greater than the area under compression, so the work done here will be positive. To easily identify this, look into your thermodynamic process cycle. It is in clockwise direction, so the work done here is positive. So these are the ways to identify it easily. Please do remember. Let's get into the problem. So our first problem is an ideal gas is taken around the cycle ABCA as shown in the diagram. So they are given a PV diagram. The net work done by the gases. So they are asking the work done. Just few seconds before we saw that work done is equal to area enclosed by the curve. So here your area is enclosed by a triangle. So area of triangle is half into base into height. Here your base is 2V1 and your height is 3P1. So substituting it, you will get your work done as 3PV1. So it's easy, right? So our next problem, the variation of pressure with respect to volume is given by P is equal to 3V square plus V plus 25 Newton per meter square. Find the work done in the process if the volume changes from 3 meter cube to 6 meter cube. So here we have to find the work done. The work done in the form of integral is W is equal to integral P dV. So they are given a relation for P. So substitute it. Your limits will be from 3 to 6 because the initial volume changed from 3 to 6. So integrating it and substituting the limits, you will get your answer as 277.5 joules, approximately 278 joules. The next problem, in a thermodynamic process, the pressure of a fixed mass of a gas is changed in such a manner that the molecules give out 30 joule of heat and 10 joule of work is done on the gas. If the initial internal energy of the gas is 40 J, then what is the final internal energy? So they are asking our final internal energy. So by the first law of thermodynamics, delta Q is equal to delta W plus delta U. They are given delta Q as 30 joule. But why negative sign? Because the heat is given out. So delta Q is minus 30 joule. Sign convention is important, I said you right. Next is delta W is equal to minus 10 joules. Why? Because the work is done on the gas, that is work is done on the system, so it is negative. So by substituting the values, you will get delta U as minus 20 joule. And delta U is U2 minus U1. Your U1 is 40 joule. By substituting it, you will get your final internal energy as 20 joules. The next problem, 1 mole of a monatomic perfect gas initially at temperature T0 expands from V0 to 2V0 at a constant temperature and constant pressure. So these are two cases. Calculate the work done and the heat absorbed by the gas in each case. So our first case we are taking here is constant temperature. If it is constant temperature, our thermodynamic process is isothermal. So for isothermal, your work done is delta W is equal to nRT ln Vf by Va. So initial and final volume they are given. So 2 V0 by V0. So your final work done will be delta W is RT0 ln 2. Next, delta Q is equal to delta W plus delta U. For your isothermal process, always your delta change in internal energy is 0. So your delta Q will be RT0 ln 2. Next is for constant pressure. Here by first law of thermodynamics, delta Q is equal to delta W plus delta U. So we know delta U is equal to NCV delta T. They are given 1 mole of gas. So N is 1 and delta U is CV delta T after substituting N. How to get CV? They are mentioned there a monoatomic gas. So we can find the gamma value. So for monoatomic gas, degree of freedom F is 3. So by substituting it, you get gamma as 5 by 3 and CV is equal to 3 by 2 R. So substitute the CV value, you will get delta U is equal to 3 by 2 R delta T. Next is work done. So delta W is equal to P delta V. So change in volume is 2 V0 minus V0 is V0. So delta W is equal to P V0. But look here, your delta W and delta U are not in same terms. So we have to convert this. So we know ideal gas equation P is equal to nRT. So P delta V is equal to nR delta T. So after substituting this, our delta W will be equal to R delta T. Now both delta U and delta W are in terms of R delta T. So substituting this, our delta Q that will be equal to 5 R delta T by 2. So I am extending this for problem a bit. So what if they ask to find the final temperature? So by the ideal gas equation, PV is equal to nRT. So initially our initial volume and initial temperature are V0 and T0 and final volume they have given us 2 V0. Let me consider my final temperature as T. So divide these equations. Your P and V0 gets cancelled and NR gets cancelled. So finally 2 will be equal to T by T0, that is T is equal to 2 times T0. So your final temperature is twice the times your initial temperature. So this is just to give you an idea how the questions can be. And the last problem, when an ideal monatomic gas is expanded from initial volume V0 to 3 V0, its temperature from T0 to T, then the ratio of T by T0 is. So here how to proceed for this problem. Here I want you guys to think for this problem. So I will be giving the options for this question. If you try and get your correct option, please do post it in the comment section. Let me see how many of you are getting the answer. And I will be doing this problem as first one in my next problem series video. I want you all guys to give a try for this problem. That's it for the day. Thank you everyone. Keep supporting. Bye bye. Have a nice day.